Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is actual vapor power cycle. This is the 23rd module of the course Thermodynamics and its application. After listening to this video lecture, you will be able to understand the concept of actual vapor power cycle. You will be able to know the piping and condensation losses in actual vapor power cycle. You will be able to explain the boiler, turbine and pump losses in actual vapor power cycle, and you will be able to solve the numerical related to Rankine cycle. In our earlier discussion, we had discussed Rankine cycle, the ideal vapor power cycle, but in actual practice, the actual vapor power cycle are different from the ideal vapor power cycle because of the irreversibilities in different components. So today we will discuss about the actual vapor power cycle. We will be able to know what are the losses occurring at different components like boiler, turbine, condenser and pumps. Actual vapor power cycle is different than ideal Rankine cycle by observing various irreversibilities associated with components of the two systems. The ideal and actual vapor power cycles are shown in figure 1. It can be observed that the deviations of actual pumps and turbines from the ideal isentropic ones can be properly accounted for by using adiabatic efficiencies. This is the diagram for steam power plant where you can see the various losses. So there are 4 important components are there in steam power plant. Those are boiler, turbine, condenser and pump. Boiler is producing high pressure, high temperature steam, and that high pressure, high temperature steam is entering into the turbine, and in turn the turbine does the work WT. So WT is the work done by the turbine. After that, the low pressure and low temperature steam coming out from the turbine and entering into the condenser. So in the condenser, the heat is giving out to the outside, that is Q2, and the low pressure, low temperature steam is converting into water. Then pump is pumping that water to the boiler and thus completes the cycle. Inside the boiler, coal is burned and the heat evolved is utilized for converting water into the high pressure, high temperature steam. But you see that there are losses in the process. There is heat loss in the turbine, in the condenser, in the pump, and of course there are several losses apart from heat loss inside the boiler. We will discuss those things in detail in our next part of our discussion. This diagram, that is TS diagram, temperature entropy diagram for the cyclic process for actual and ideal vapor power cycle. The dotted line depicts the cycle diagram for the actual Vapour power cycle, whereas the solid line is depicting the actual cycle. You see that in the boiler there is pressure loss, in the condenser there is pressure loss, and due to the irreversibilities in different component of this Vapour power cycle or the steam power plant, we get less work in the turbine as an output, and we have to put more work in the pump. Now from this diagram you see that one is the entry point of the steam in the turbine, and that point 2 is the exit point of the turbine, but we are supposed to get the work output, that is H1 minus H2S, but in practice we are getting less output from the turbine because of the irreversibilities in the process which is occurring inside the turbine. Same thing is happening for pump, and there are losses in the condenser and the boiler, and we will discuss in detail those parts in this today's discussion. Now this diagram gives the effect of pump and turbine irreversibility on the ideal Rankine cycle, and this is the comparison that the work output in the turbine we are getting in actual practice H1 minus H2A, whereas in isentropic process we are supposed to get the work output from the turbine is H1 minus H2I. So the component efficiency of the turbine is the work output in actual practice divided by the work output as in the isentropic process. So the eta T, that is component efficiency of the turbine, is defined as H1 minus H2A whole divided by H1 minus H2I. The same we can do it for the pump. So for the efficiency of the pump or the component efficiency of the pump is H4I minus H3 whole divided by H4A minus H3. This can be clear if you see the picture. The various effects of irreversibilities associated with pump and turbine on the ideal Rankine cycle is as shown in figure 3, in which 2I and 4I are the isentropic exit states of the turbine and pump respectively, and 2A and 4A are the actual exit states of the turbine and pump respectively. And why this difference? Because there are irreversibilities in the processes. Piping losses. Pressure drop due to the friction and heat loss to the surroundings are the most important piping losses. Turbine losses. The losses in the turbine are those associated with frictional effects and heat loss to the surroundings. Pump losses. The losses in the pump are similar to those of the turbine and are mainly due to the irreversibilities associated with fluid friction. Condenser losses. The loss in the condenser is usually small. These include the loss of pressure and the cooling of condensate below the saturation temperature. Now this diagram depicts the different losses in the boiler. Suppose the heat input in the boiler is taken as 100% and we are getting the high pressure, high temperature steam, but that output which we are getting from the boiler is around 69.1% because there are losses inside the boiler operations. Now let us see what are the losses occurred inside the boiler. For this case, around 13.7% is heat loss due to the dry flue gas. 8.6% is heat loss due to steam in flue gas. 2.7% is heat loss due to moisture in fuel. 0.8% is heat loss due to the moisture in air. 3.4% is heat loss due to unburnt in residue, and 1.8% is due to heat loss, radiations and other unaccounted losses. So there are several losses. So if 100% is the heat input in the boiler by burning of fuel, there are several losses in the boiler operations, and if you consider those losses, definitely the output from the boiler will be less, and for this case it is around 69.1%. Now let us solve an exercise. This problem is a very interesting problem, and let us see how we can proceed for this problem. But I have already given the guidelines for solving any problems related to thermodynamics, and those guidelines are that first of all you have to note down the data given for a particular problem. So let us go through this problem and we will see how we can solve this problem. Steam at 30 bar 400 degrees centigrade is expanded in a steam turbine to 0.08 bar. It then enters a condenser where it is condensed to saturated liquid water. The pump feeds back the water into the boiler. A. Assuming ideal processes, find per kg of steam the net work and the cycle efficiency. B. If the turbine and pump have each 85% efficiency, find the percentage reduction in the net work and cycle efficiency. Now let us see what data is given for this problem and what information we can get out of that data. The property values at different state points in figure 5 found from the steam table are given below. Now H1 is 3230.8 kilojoule per kg because the pressure is given and temperature is given. Before entering into the turbine, the steam was superheated, the pressure is given, superheated temperature is also given. So we can calculate the enthalpy at state 1, that is H1, that we get from the steam table, and here the value of H1 for this particular pressure and temperature is 3230.8 kilojoule per kg. The entropy at the point 1, that is S1, is equal to 6.922 kilojoule per kg K, and H3 equal to 173.88 kilojoule per kg, and S3 we get 0.5926 kilojoule per kg K. This is corresponding to the saturated liquid line, and HFG is 2403 kilojoule per kg, and the entropy at that particular point is 8.2287 kilojoule per kg K, and the specific volume at point 3 is 0.001008 meter cube per kg, and entropy at that point is also known. Now we know very well that S1 is equal to S2S, so we can calculate the quality at the point S2S, that is X2S is equal to, for this particular case, is equal to 0.8287. Now this is the diagram for this particular problem. Now here the initial pressure is 30 bar and temperature is 400 degrees centigrade, and 2 is the actual exit from the turbine, and 2S is the isentropic work exit from the turbine. So once you know H1, S1 at the point 1 at the exit point, and for an isentropic process, that we can write that S1 is equal to S2S. Now S1 you can get from the steam table, and H1 you can also calculate from the steam table. Now if you write S1 and S2S, and H2S is equal to H3 plus X2S multiplied by HFG3, that you will get from the steam table. So you can calculate the value of the dryness fraction, that is X2S. Once you calculate X2S, you can proceed further. Let us see how we can solve this problem. Once you calculate the dryness fraction, that is X2S, so we can easily calculate H2S, because you know HL at that particular pressure, that is enthalpy at the liquid line. You can calculate the HLG, so you can calculate H2S, that comes out to be, for this particular problem, is 2166.05 kilojoule per kg. Now the pump work, that is WP, is equal to H4S minus H3. So that you can get if you know the specific value for that particular point at 3. So that is given for this particular problem, that is 0.001008, and you know very well the pressure difference P1 minus P2, so we can calculate the pump work, that is WP, is equal to 0.001008 multiplied by 29.92 into 100, that comes out to be 3.01 kilojoule per kg. So H4S you can calculate, that is 176.89 kilojoule per kg. So WT is equal to H1 minus H2S, that you know H1 you have just calculated H2S, so there is no problem for calculating WT, that is work done by the turbine. So that WT is equal to 1064.75 kilojoule per kg. Now W net is the net work done for this process, is equal to WT minus WP. You know WT, you know WP, so W net is equal to 1061.74 kilojoule per kg. Now Q1 is equal to H1 minus H4S. So you know H1, you know H4S, so there is no problem for you to calculate Q1, that comes out to be 3053.91 kilojoule per kg, and eta cycle is equal to output by input, so eta cycle is equal to 1061.74 whole divided by 3053.91, that comes out to be 0.3477 or 34.77%. Now it is given that the pump efficiency and the turbine efficiencies are 85% each. So WP is equal to 3.01 whole divided by 0.85. So WP for the actual process is equal to 3.54 kilojoule per kg. Similarly, we can calculate the actual work done, that is WT is equal to 0.85 multiplied by 1064.75, that comes out to be 905.04 kilojoule per kg. And in this case, W net is equal to turbine work minus pump work, that is WT minus WP, that is equal to 901.5 kilojoule per kg. Now, reduction in work output is 1061.74 minus 901.50 whole divided by 1061.74, that comes out to be 0.15092 or 15.09%. Now see that H4S is equal to 173.88 plus 354 is equal to 177.42 kilojoule per kg, and Q1 is equal to 3290 minus 177.42, that comes out to be 3053.38 kilojoule per kg, and eta cycle is equal to output by input, that is 901.50 whole divided by 3053.38, that comes out to be 0.2952 or 29.52%. So reduction in cyclic process is 0.3477 minus 0.2952 whole divided by 0.3477, that comes out to be 0.1509 or 15.09%. So dear learners, you might have understood how we can tackle any problem in thermodynamics. The basic thing is this, that first of all you have to go through the numerical and you have to note down the data given for that particular problem. Then you proceed systematically, and I am sure that you can solve any problems on this thermodynamics vapor power cycle topic. So let us summarize our discussion. We have discussed the concept of actual vapor power cycle. We have seen that actual vapor power cycle is entirely different than the ideal vapor power cycle. There are losses, there are irreversibilities in the processes which are there in the whole vapor power cycle processes. There are irreversibilities in turbine, in condenser, pump, and also there are several losses in boiler. Therefore, the actual vapor power cycle is entirely different than ideal vapor power cycle. So, piping and condenser losses also plays a vital role, because of which there is a deviation from the ideal vapor power cycle, and we are getting the actual vapor power cycle which is entirely different from the ideal vapor power cycle. We have discussed the boiler, turbine and pump losses in actual vapor power cycle. We have also solved a numerical related to the actual vapor power cycle. So thank you very much for today's discussion. In the next class we will discuss some more interesting topic on the thermodynamics and applications course. Thank you very much.